folks. So as I wrote in the document that you can see right in front of you, this is a POGL, so it is designed to be done on your own. I think the questions are not as straightforward and that they require a little bit of explanation, so I think it would be kind of hard for some people to do it totally on their own, especially if they don't have a teacher to ask questions to. So it's really up to you. If you want to do it on your own, that's fine. If you want to follow along, that's fine. Just if you're following along, just write your answers in here, which we're going to go over, and then go ahead and do the rest of the document on your own. So we're going to start off by talking about this concept called dynamic equilibrium. So this is a manufacturing plant, Acme Manufacturing, and Acme Manufacturing can only have 100 employees in the plant at one time. Okay? And obviously those employees need to take breaks. So throughout the day, 20 employees will go on break and then 20 employees will enter so that we stay at 100 inside the plant. Okay? Question, you can ignore this chemical equilibrium for right now. We'll go back to that in a minute. So for question number 1 says, how many employees go in and out of the building each hour? So 20 employees go in and 20 employees go out. So it's a total of 40. So the answer here would be 40 employees go in and out of the building. Are the employees who move in and out of the building each hour the same people? No, they are not. So every hour, a different set of 20 employees takes their break. It's not like the same 20 employees get a break and no one else does. Okay, so at every different hour, 20 people will come out and 20 people will go in. Number 3, does the number of employees in the building change from hour to hour? So that's talking about how many are actually in the plant, which is always 100, okay? So once you hit 100, it stays at 100. So every time some people come out for their break, other people can enter, but the building has to stay at 100. It's a little bit like grocery stores right now. If you have been to a grocery store or your parents have been, grocery stores have a certain amount of people that are allowed in them right now. And so you see the lines outside the grocery stores, and then those people cannot enter until other people leave. So let's say their limit was 100, like Acme Manufacturing. You stand outside and you wait, and then when one person leaves the grocery store, one person can go in the grocery store, and it goes back and forth that way. So it's different people. Obviously, they're not going to stay in the grocery store all day. They go in and they go out, they get their food, and then they leave. And so it's different people going in and out at the same time. So that brings us to number 4. Over the course of the day, the employees in the Acme manufacturing plant are said to be in a dynamic equilibrium. Based on your understanding of how the staff move in and out of the plant, explain what is meant by the term dynamic equilibrium. So obviously you can do this in your own words. I'll try my best to explain it. So there are 2 parts to this term, dynamic and equilibrium. Equilibrium is something that we're going to maintain, okay? So equilibrium in the case of the Acme plant is the 100 employees inside the building. Okay, once you hit 100, it stays at 100. So like during the morning, people are coming in, I guess it could be at like 75, it could be at 80, you have to build up to that. But once you get to what we call equilibrium, you maintain it. So once you get to 100, you maintain it. Okay, so that's the equilibrium part. Dynamic means that doesn't mean that those 100 people are now stuck in the building for the whole day. Dynamic means there can be some movement. So when people come out of the building, other people can go in. So even though we're always at 100, we're not necessarily always at the same 100 people. Okay, so some people come out for their break and other people go in for their break. So that's what the dynamic part means. It means movement. Some will move in, some will move out. So now we're going to apply that to the reaction. Okay, so the reaction we're going to be looking at is this one right here. And it just looks like a normal reaction, but you might notice that there's a little bit of a weird arrow here. This is a double-headed arrow. So what that arrow means is that this reaction is reversible. We can go this way, or we can go in the reverse direction. okay? And reversible reactions will hit equilibrium, okay? And when they're at equilibrium, we want to maintain that, okay? So it's the same deal as the plant. Once they hit equilibrium, once they hit 100, we're going to maintain that, all right? So keep that in mind as we go through. When the reaction between hydrogen and oxygen reaches equilibrium, so going back to the plant, that means it's at 100, okay? So reaches equilibrium, we want to maintain it. Does the number of molecules in the reaction vessel change? So this is just taking our Acme plant and changing it into a chemistry situation. So number of molecules here would be the people. The reaction vessel would be the plant. So we've already answered this question if you rephrase it. Does the number of molecules in the reaction vessel change means does the number of people in the plant change? And the answer was no. Okay, we said there was 100. All right, we cannot have more than 100. So once we reach 100, we stay there. Is the reaction still proceeding in the forward direction? Yes, it is. Are people still going into the plant? Yes, they are. Is the reaction still proceeding in the reverse direction? Yes, it is. Are people still leaving the plant? Yes, they are. So the B and C here are getting to that dynamic idea. So A is about equilibrium, maintaining it. And B is saying that we can still go forward and we can still go back. It's the dynamic part. And then that brings us to D. Are the concentration of the products in the reactants changing? No. We're going to keep those concentrations the same. Okay? Which brings us to E. Are the rates of forward and reverse the same? Yes, they have to be, okay? So that's going back to the people in the plant or the grocery store. The people entering the plant need to be at the same rate as the people leaving the plant, or you would have more or less than 100 at some point, right? So if 1 or 2 people enters, then 1 or 2 people needs to leave. If 5 people enter, then 5 people need to leave. It needs to be the same rate in order to maintain that 100 inside the building. Does the heat content of the system become constant? So what you might have noticed is that up here we had heat or energy, you can think of it as temperature as well, as a product. And so when it asks the heat content, it's basically asking the same question that we had about the concentration. Okay, so if the concentration is staying the same, that's the amount. So the amount of H2, the amount of O2, and the amount of H2O is the same. So that means the amount of energy or heat is the same. Okay, so they're all constant at equilibrium. So the answer to F would be yes. So now that we kind of understand a little bit about equilibrium, let's talk about Le Chatelet's principle. So Le Chatelet's principle takes equilibrium and says, okay, well, what if I change something? So what we call the change in Le Chatelet's principle is the stress. So what if we take a system that's at equilibrium and we do something to it? Okay, so this is going to be our system that we just, the same one as above. And what if we changed something? So here are the list of things you can change and what the effect would be. All right, so if you add some of a product, some of a reactant, if you add some of a reactant, you're going to want to get it back to equilibrium. So you're going to need to, so if we added some of this H2, we would need to go and make some of this H2O to balance it out, okay? So if you added O2, same thing. You would make H2O, you would add some energy, you would go in this direction to balance it out, okay? So that's what this is saying. If you increase the reactant, it causes the equilibrium to shift to the right. You have too much on this side, so you need to balance it out by going to this side, okay? So if you think of it, you need to go this way, okay? If you decreased the reactants, if you had less on this side, you would need to go towards that. So it would it would shift to the left. Okay, so again, if you increased the product, so let's say we increased H2O, And that just means we added more of it. That's the stress. If we increased H2O, then we would need to go this way to balance it out by making more of this stuff. If we decreased H2O, then we would need to go to the right to make more of that H2O. Okay, so you're just trying to keep a balance. So if you have too much on one side, you need to shift towards the other side to make that balance again. So now let's talk about temperature. Temperature is like a reaction or a product. So if we add energy, if we increase the temperature, we're going to shift the other way because that's increasing a product. So we would shift to the left. If we decrease the temperature, if we decrease the energy, that means we would shift to the right, just like here, because here in this reaction or in this system, energy is a product. You can also have energy as a reactant, but here we don't. We have it as a product. So we would go with the product rules for temperature. So that brings us to pressure. Now pressure is a little bit different because pressure you have to measure the moles of gas. So let's just read what it says. An increase in pressure causes the equilibrium to shift towards the smaller number of moles of gas. A decrease in pressure causes the equilibrium to shift towards the larger number of moles of gas. Okay, so what you do is you look at your reaction. Here, everything is a gas, all right, except for the heat. But everything is a gas. Now, in some reactions, you might have some liquids, some solutions, some aqueous, some solids, and then you just ignore those for purposes of pressure, so you can just ignore them. But here, everything is a gas. So let's count the moles we have. So here we have 2 moles of H2. Remember that the coefficient tells you the moles. So we have 2 moles of H2 here, 1 mole of O2 here. So we have a total of 3 moles of gas over here. Okay, here we just have the 2 moles of gas because the energy heat doesn't matter for this. So here we just have 2 moles of gas. So what this is saying is if you increase the pressure, it goes towards the smaller number of moles of gas. So we would go towards the 2, and then decrease, we would do the opposite, which we're going to do now. So now what I'm going to do is give you some examples of if we had this stress, what direction would we shift the equilibrium? So H2 increases. So H2 is right here. It is a reactant. So if H2 increases, you increase a reactant, that causes the equilibrium to shift to the right. And that makes sense if you think about it in the other way that we were talking about it. We would have too much on this side. So to balance it out, we have to go in this direction. Okay, to get to get back to equilibrium. So the next one, O2 decreases. So O2 is also a reactant. If we decrease a reactant, decrease causes the equilibrium to shift to the left. Okay, so we can go ahead and write a left here. And a lot of times you'll see arrows for this. It's just easier to write right or left or R or L on the computer. So that's what I'm doing for you. So again, that makes sense because if we decrease this, we would have less on this side. So we would need to go here to make it balanced. So now H2O, if we decrease H2O, H2O is a product. So we would go decrease, causes the equilibrium to shift to the right. So we write R. Okay, so that makes sense again because we have less of this, so we want to balance it out by going in that direction. Temperature increases, so temperature is right here, and the temperature rules say you treat it as a reactant or a product. So here it's a product. So if we, sorry, I forgot what it was. If we increase a product, increase the reaction, we increase, it causes the equilibrium to shift to the left. So this would be left. And then our last one is pressure. Pressure decreases. So pressure decreases. A decrease in pressure causes equilibrium to shift towards the larger number of moles of gas. We already counted the moles of gas here. So we said we had 3 on this side, 2 plus 1. And then we had 2 on this side. So if we decrease the pressure, we're going to shift towards the larger number, which is obviously 3. So we would go towards the reactants, or to the left. And that's equilibrium. So there's another really short video that just talks about how to do, or how the virtual lab down here works. So what you should do now is just answer these questions, which are very similar to the ones that we just did together. And then there's a virtual lab that's kind of, it's just not self-explanatory how to do it. It's very easy, but I just wanted to go over how to do it. So there's another quick, I think it's less than 3 minutes video on how to do that, and then a simulation.